Okay, before I go to the proof of above theorem, I would also like to give couple of remarks about Zorn's lemma. So, namely, see, one can prove Zorn's lemma by using axiom of choice. So, let me briefly recall axiom of choice, which is more intuitive statement, which is very easy to believe, but it is also equivalent to Zorn's lemma. So, axiom of choice. So, let us recall, if you have given a family AI of non-empty sets, there exist a function C from the indexing set I to the union AI such that the image of any I under C of I should belong to the corresponding set AI. Such a function is called a choice function. So, we are making a choice and picking up elements from AI and then we are mapping I to the AI. So, such the existence of axiom of choice is precisely a statement which says given a family of non-empty sets, there exists a choice function. For this family. So, this Zorn's lemma what I have stated above is equivalent to this axiom of choice, and this axiom of choice restatement is precisely. So, this is equivalent to saying the product set AI, this is non-empty, that is axiom of choice, because an element of the product set is a tuple and the tuple will give you the function. So, if there is a tuple here, that will correspond to a choice function. So, the normal course on abstract set theory will have such implications. Axiom of choice is equivalent to Zorn's lemma, and also equivalent to another useful theorem which is called Zermelo's well ordering theorem. The Zermelo's well ordering theorem says that every set can be well ordered. That means on every set we can put an order which is a well order. That means well order means every non-empty subset of that set has the minimum. So, first though this is an abstract theorem, given any set A we can define an order on that, we can construct an order which is a well order. This construction is not explicit, this is an abstract construction, and even for the uncountable sets explicit constructions are not known. even on the set of real numbers. We know this usual less equal to, this is an order, this is a totally ordered set, but this is not well order, because if you take a set like subset like open intervals 0 1 for example, this is a subset, the minimum or even whole set real numbers, even if you take a set of real numbers, there is no minimum. So this usual order is not a well order. But Zermelo's theorem says that there exists a well order on R, but how to explicitly construct, that is not known. Okay, so so far now I am going to use this Zorn's lemma. Zorn's lemma is the most handy way to check some ordered set has maximal elements or not. And once you have maximal, also you can infer about minimal elements by proving the theorems to the opposite ordered set. So it is usually one only concentrate on the maximal elements. So okay, so let us come back to the proof of the theorem we stated. Proof of theorem. Remember, what we need to do is we have given a generating system and we have given a part of that generating system which is linearly independent, and we want to maximize this, we want to put a maximal. So we have to come to a situation, we have to extract from this, we have to get a ordered set which should be inductively ordered, and then use Zorn's lemma to conclude there is a maximal element there, and this maximal element should be the required basis. That is the idea. So consider a set script J, I will call it. This is by definition, I collect all those J primes in Pi in the power set of I. That means all those subsets J prime of I such that J should be contained in J prime and the family X J prime in J prime. So the J prime is, remember this is in Pi, mean this is contained in I. This is K linearly independent. So the scripts J is precisely all families of the given generating system which contain the linearly independent family, subfamily, and it enlarged to a linearly independent family. These are precisely J prime. And so by assumption that this set J belongs to J, the script J, because we have given the subfamily index by the J is linearly independent. So that means the J belongs to J prime. Now the J belongs to script J. This is by assumption. Okay. Now I want, so the J script J is obviously ordered by natural inclusion. This is unordered set. The J is this natural inclusion is, this is natural inclusion. And we want to check that this ordered set has maximal elements. We want to prove that J has maximal elements. For this we want to use Zorn's lemma. For this we need to use, we will use John's lemma. But for this we need to check the assumption given in John's lemma. We need, for this we need to check that this ordered set J inclusion, this is inductively ordered. That means every chain in this script J has an upper bound. So that means we want to check that every chain C in this ordered set has an upper bound. Okay, so first let us take, suppose C is empty chain, then obviously the J which was given to us in assumption, that is an upper bound, is an upper bound. For C. You note that upper bound just means it should contain every element of C. See, elements of C are subsets. So upper bound means a subset which is in J, but it should contain all elements of C. So that is an upper bound for C. So suppose C is non-empty, then I am going to look at the union of all elements in C. This one. Note that because C is non-empty, this union makes sense. C were empty union will have problem. So because C is non-empty, this J prime makes sense, and it obviously contains, it's a subset of I and obviously contains J, because each J prime is in C and C is a chain in this, and all elements of J contains J. So therefore J is a subset of J double prime and J double prime is a subset of I. Now we also, it is clear that J double prime is an upper bound. For C. But only to check, therefore, only to check that the J double prime should also be in script J. Then only it is an upper bound for C in J. So we have to verify now that J double prime is in the script J. But J is contained in J double prime, it's a subset of I. So therefore only thing to check, only real checking is, so only to verify that the subfamily X J double prime, as J double prime varies in J double prime, is K linearly independent. Because this will ensure that J double prime is indeed an element of script J. That was the definition of J, script J. So we want to verify that this family is linearly independent. Okay, so what does that mean? That means if you have a linear dependence relation, then all coefficients are 0. Okay, so suppose you have a dependence relation like this: a j double prime x j double prime is 0. This sum is varying over j double prime in j double prime, and obviously a j double prime, this tuple j double prime in j double prime, this is in k upper bracket j double prime. This, as usual, this simply means only finitely many coefficients are non-zero. So, look at this set, although j double prime for which a j double prime is non-zero. This is some subset of j double prime, and this is a finite set. This is a finite subset of that j double prime, because only finitely many of them are non-zero. And what we want to prove is this set is actually empty set. Let us call this set as what can I give name? Let us call this as j tilde or j double prime tilde. So, we need to prove that j double prime tilde is empty set. That means all aj double primes are 0, and then we would uproot that they are linearly independent. Okay. So, suppose it is not, then we should lead to contradiction. So, suppose j double prime tilde is non-empty, but it is a finite set and they are all elements of j double prime, and j double prime. So, now I want to use the fact that the j double prime is the union of j prime. The j prime is varying in C, and I want to use this fact that C is a chain. That means, if I have given a finitely many elements in j double prime, they will belong to this union, finitely many elements, but among the j double prime when j prime is varying in C, so they have a inclusion relation among them. So, by without loss of generality, this j double prime tilde will be contained in one of the j prime. Not this is wrong, but without loss. So, because j double prime is finite and C is a chain, it follows that the j double prime tilde will be in one of the j prime. Because if, for example, if j double prime has only one element, this is obvious. If j double prime has more than one element, they will belong to two different j primes, but the j primes are comparable. So, I will choose a bigger one. So, definitely this, but then this relation will become a dependence relation. So, but then this a j double prime x j prime equal to 0 is a dependence, is a linear dependence relation among x j prime, j prime is in j prime, which contradicts, this contradicts this contradicts the choice that j prime belongs to script j. So, that proves what we wanted to prove, that proves that I can enlarge a given linear independent family to a maximal linear independent family, and by then previous lemma it is a basis. Okay, so that proves the theorem that we wanted to prove. Now I want to write one corollary. Okay, so one corollary I want to write. Okay, corollary is as usual V is a K vector space. In this corollary I have collected the special cases of the above theorem which will be handy to use. So, and W be a subspace of V. Then 1 every generating system for V contains a basis, K basis of V. Because take the generating system and find a maximal linearly independent subset by the above theorem, and this must be a basis. Okay, so second, so this I will write here. This is a special case. I will write with the blue in the bracket here. This is a case where J is empty set in the theorem. Because that empty set is linearly independent and you make it maximal by the theorem, such thing exists, and that is a basis. So, okay, so V as a basis. V as a basis. So, these two, 1 implies 2 is clear. So, 1 is the special case J equal to empty set in the theorem. Third one, every basis, every K basis, K basis of W can be extended to a K basis of V. So, K basis of V is linearly independent family of W, but if it is linearly independent family of W, it is linearly independent in V also. So, apply again the theorem to this. So, 4, there exists a basis K basis of V which contain a K basis of W. So, this is also a restatement of 3. So, now I just want to give one remark here. So, remark, so suppose I have a field extension. So, let capital L over capital K be a field extension. That simply means, so that is K is a subset of L and it is a subfield. That means the operation in the plus and product multiplication operations in K are restrictions of the additions and multiplication in L. A typical example is Q contained in R. So, R is a field extension of Q. Similarly, C is a field extension of R, or C is a field extension of Q. So, field extensions are very important in the study of theory of equations, and for field extensions you also need to use a vector space argument many times. So then what we have just proved above, that L, if you look at L as a K vector space, it has, so L has a K basis which contain 1. 1, remember 1 is same thing as 1 of L, or 1 of L is same thing as 1 of K. Multiplicative identities are same because it is a subfield. So, we can extend, this means you can extend the set 1. Remember 1 is linearly independent over K, and this linearly independent set we can extend it to basis by the earlier theorem. This is very important. Okay. So, such a basis, such a K basis in the case, so in the is also called Hamel basis. Of L over K. Hamel was the first, Hamel proved this for the case K equal to Q and L equal to R. This was proved in the beginning of 20th century. So, with this also people in general now this is very common language in, especially in function analysis in general, where the not finite dimensional vector spaces are involved. In general, if V is a K vector space of not of finite, so of dimension not finite dimension, not of finite dimension, then we have just put that V as a K basis, the K basis of V are also called Hamel basis of V over R, V over K. Remember, lot of spaces we have dealt in the examples above, namely n times continuously differentiable real valued functions and say a closed interval. This is a R vector space and this is not finite dimensional. So, we know by abstract theorem this has a basis, and one can also prove that the basis actually is not countable. So, such bases are called Hamel basis. Okay. So, Now still we need to prove the following theorem. So like a finite dimensional case, so we now need to prove, okay, I will just say it orally. We now need to prove that any two bases have the same cardinality. Now for this we will do this in the next lecture, but for this I will have to recall a little bit more precisely the concepts of cardinalities and how does one prove the two sets have same cardinalities or not. This we will do it in the next lecture. Thank you.